Hello everyone, for this tutorial video, I'd like to talk about the tangent and normal vectors for vector functions, and exact formulas / equations for them. As we can recall from Calculus 1, the derivative is the slope of the tangent line, so it should follow that for vector functions, because of how vectors are represented with lines, that the tangent must be a derivative vector. So we state that the derivative of the vector function is exactly the tangent vector. And you can convince yourself this is true by drawing or graphing out a vector function, then calculating the derivative by taking the derivative of the individual components, and then graphing out the result and seeing how the result is tangent at the particular point you choose. One caveat besides the derivative needing to exist is that the derivative cannot be 0, because if the derivative would be 0, then that would mean the tangent would have no magnitude or it would not exist. If we want a tangent vector of a magnitude 1 specifically, we would get this by taking the normal tangent vector and then dividing by its magnitude, and this is the formula for the unit tangent vector. Using the unit one rather than a traditional tangent vector is useful for figuring out the rate of change of a vector function using a more universal type of tangent instead of tangents with different lengths, so it is more predictable with a unit tangent versus the traditional one. The unit tangent is also used in the definition of the normal vector, or more specifically the unit normal vector, which is the unit tangent divided by the magnitude of it. This may seem like a bizarre definition at first, but the proof is in that if we assume a vector function r of t always has a magnitude of a constant c, then we would first compute the dot product of the vector times itself, which we remember is the magnitude squared, so this means it becomes a constant squared. We take the derivative or tangent of this dot product. We see it equals the derivative of the constant. The derivative of a constant, even if it is squared, is still 0. So now we expand the left-hand side by remembering how the product rule works in general from Calculus 1, simplifying it, remembering that we determined it was equal to 0 earlier, noticing that we can factor the constant out because the result is 0. In conclusion, the dot product of the function and its derivative equals 0, and we remember from the geometric definition of the dot product, if we have a value of 0, the vectors must be perpendicular. In conclusion, since the tangent has been proven to be perpendicular to the function itself, it follows that the tangent must be a normal vector, because we defined earlier a normal vector as perpendicular. Now that we've figured out tangent and normal vectors, we can discuss how to expand arc length to include vector functions by interpreting it as a 3D parametric curve. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.